In this lesson, we will be learning about patterns and inductive reasoning. The objective is to use inductive reasoning to make conjectures. So let's look at the vocabulary. What is inductive reasoning and what are conjectures? Inductive reasoning is reasoning based on patterns that you observe. So a conjecture is a conclusion that you reach using inductive reasoning. So it's a conclusion based on patterns that you observe. A counterexample is an example that shows that a conjecture is incorrect. It only takes one counterexample to show that a conjecture is false. Another type of reasoning that we will learn about in lesson 4 of this chapter is deductive reasoning. And I just wanted to bring it up here to contrast it with inductive reasoning, because deductive reasoning, which is sometimes called logical reasoning, is the process of reasoning logically from given statements or facts to a conclusion. So deductive reasoning is based on facts, inductive reasoning is based on patterns that we observe. So let's use inductive reasoning and patterns. In problem 1, we're going to look for a pattern. What are the next two terms in each sequence? So if we look at the first sequence, it's a numeric sequence. The first term is 4, the second one is 8, the third one is 16, and the fourth is 32. So if you look at the pattern is you're taking each term and you're multiplying it times 2. So that means that the next two terms would be 32 times 2, which is 64, and then 64 times 2, which is 128. In the B part, it's a figure that we're looking at. So let's try to find the pattern in these figures. We got to find the next two terms in this sequence. So the first one we can look at as being, if we look at the sides, this one would be 1 by 1. This one would be 2 by 2. And this one is 4 by 4. So that's one way of looking at that pattern. The next figure would be 8 by 8, which would have 64 units. And then the next figure after that would be 16 by 16, which would have 256 units. Another way of looking at this pattern would be if you look at the number of squares contained in each figure. The first one is 1 square. The second one has 4 squares. And then the next one has 16. So we can conclude by looking at this pattern that if you multiplied each one of these by 4, you would get to the next figure. So you have the 4 times the 4 would be 16. Multiply that times 4 is going to be 64. And if I multiplied 64 times 4, that would be 256. So that would be another way of looking at this pattern. In problem number 2, we're using inductive reasoning to determine what conjecture you can make about the 25th term in this sequence. 1, 2, 3, 1, 2, 3, and ... means on and on. So let's look at the pattern. The pattern is that we have 3 numbers that are repeating. So if we take the number 25 and divide that by the number of terms in the pattern. So there's 3 numbers in the pattern. Divide that by 3. 3 will go into 25 8 times with a remainder of 1. So the first term in this, the first number in that sequence in each one of these, in this pattern, is 1. So that means since there is a remainder of 1, then it's going to be the first term. So the 25th term will be the number 1 because that is the first term in the pattern. In problem number 3, we're collecting information to make a conjecture. So what conjecture can you make about the sum of the first 40 even numbers? So let's make a table. Number of terms. If we're just looking at one term, what is the first even number? So the first even number is 2. If we're looking at the first 2 even numbers, those are 2 and 4. So we're looking at the sum of 2 and 4, which is going to be equal to 6. Our first sum was just 2 because we only had one term. And then we have 3 terms. So the first 3 even numbers are 2, 4, and 6. So 2 plus 4 plus 6 is equal to 12. And let's look at one more set. Our number of terms is 4. So the first 4 even numbers are 2, 4, 6, and 8. So 2 plus 4 plus 6 plus 8 is equal to 20. So let's try to find the pattern. Let's rewrite this. Instead of writing them as sums, let's write these numbers as a product and see if we can see a pattern. So 2, if I write that as a product, is going to be 1 times 2. And 6, written as a product, is 2 times 3. 12 is 3 times 4. And 20 is 4 times 5. So let's see the pattern. The pattern is that if I wanted to know the first 40, the sum of the first 40 even numbers, then it would be 40 times 41, according to the pattern that we've observed, which is going to be equal to 1640. So if you write this in general terms, the sum of the first however many even numbers you want to sum is going to be that number times the number that follows it. So it's n times n plus 1. In the next problem, we'll be making a prediction on sales of tickets. Sales of tickets at an amusement park increased over a period of 4 consecutive months. What conjecture can you make about the number of tickets the park will sell in February? So let's look at the graph that they give us. And the tickets are basically on your y-axis, and your month is on your x-axis. And looking at the months, you can see the O is October, the N is November, the D is December, the J is January, the F is February. So February is what we're trying to predict. The number of tickets the park will sell in February. So let's just read the graph. In October, it looks like the number of tickets sold was 50. In November, it's about 150. In December, it's about 325. In January, it looks like it is 425. So we want to use these numbers to predict the ticket sales for February. So let's look at the pattern. If you take the first number, 50, and add 100 to it, that would get you the next number, 150, in November. So now if you take the November number of 150 and you add 175 to that one, then that would give you the next number, 325. So take the 325 and add 100. That will give you the next number, 425. So based on this pattern of adding 100, adding 175, adding 100, it would appear that you would take the 425 and add 175 to get your prediction for February, which is going to be about 600. So the answer to the problem is that the park will sell about 600 tickets in February. In the last problem, we're finding a counterexample. Remember, it only takes one counterexample to prove that a conjecture is false. The first conjecture states that if an animal is green, then it is a frog. So your counterexample can be any animal that's green, but it's not a frog. So the counterexample would be a turtle is green, but it's not a frog, so that's a counterexample. B states that any three segments form a triangle. Well, there are lots of examples that we can come up with where that's not true. So let's just think of one. One would be if one side of the triangle is 3, another side is 6, and the other side is 10. That will not form a triangle. We will learn later that any two sides of a triangle, the sum of the lengths of any two sides of a triangle has to be greater than the third side. So here, 3 and 6 add together to be 9, and 9 is not greater than 10. So there's no way that those three sides could form a triangle. The last one states that when you multiply a number by 2, the product is divisible by 4. So let's look at, like I said, once again, lots of examples of this, but one example is that 3 times 2 is equal to 6, but 6 is not divisible by 4.